This is a video on scientific notation and significant figures. Now, scientific notation you're going to use a lot. It just makes numbers a lot easier to write. For example, if you look at the number of stars in the universe, these are numbers that scientists actually deal with. It's a big number. If we're going to write it in scientific notation, it's about, the squiggly lines mean about 1 times 10 to the 23rd. So that's 1 times a 10 with 23 zeros, the one with 23 zeros following it. That's a really big number. We don't want to write that in regular notation. We don't want to have to go 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, doing that 23 times every time we use a number. So we use scientific notation. It's also good for really short numbers, really small numbers when we're working on the atomic scale, for example, because otherwise you have like a 0.000000, and those numbers are hard to work with. So we use scientific notation. Now, scientific notation, hopefully you're familiar with, from other classes, from math classes, and I encourage you to brush up on it in the textbook as well. So this is just a quick overview of scientific notation. But when you're doing scientific notation, you're always working with one number before the decimal point. So let's say you have the number 340, and you want to turn that into scientific notation. Well, you're looking for the decimal point after the first digit. So you're going to want the decimal point right there, which means in order to get 340, you've got to move the decimal point 2 places to the right, multiplying it by 100. So 340 is actually equal to 3.4 times 10 to the second. Now I didn't put that 0 in there because of significant figures, which we're going to talk about a little bit later. But 3.4 times 10 to the second is the same as 3.4 times 100. And if you multiply 3.4 times 100, you end up getting 340. But we often will use scientific notation. Let's say you have the number 0.0034, and you want to turn that into scientific notation. Well, you need to get the decimal place after the first non-zero number. So you're going to still have a 3.4, and the question is how many decimal places do you have to move it? Well, from there, 1, 2, 3 backwards. People often will make a mistake and put the decimal point there and say it's 2 backwards, it's really 3 backwards. And if it's backwards, we're going to use a negative sign, so times 10 to the negative 3. That's scientific notation. If you want to reverse this and work from scientific notation to standard notation, you could say 3.4 times 10 to the 5th, for example. 3.4. So you can start with a 3.4, but you got to move that decimal place 5 spots. So you can go 1, 2, 3, 4, 5. You put a 0 each of those. So you end up getting 340,000 or 340,000. It's 3.4 times 10 to the negative 5. You're still starting with 3.4 there, but you're now moving the decimal point in the negative direction 5 spots. So 1, 2, 3, 4, 5. And you end up getting an answer of 0.00034. Take that out there. So that's scientific notation. If you're multiplying scientific notation, let's say you have 3 times 10 to the 3rd multiplied by 2 times 10 to the second. You can actually just add those exponents and multiply the numbers. So you can get 3 times 2 times 10 to the 3 plus 2. So you'll end up getting 6 times 10 to the 5th, which is 600,000. And you can put this into your calculator to verify that if you want. You can subtract as well if you're dividing, so something like 3, let me change the numbers just a little bit. 6 times 10 to the 3rd divided by 2 times 10 to the 2nd. You end up getting 6 divided by 2 times 10 to the 3 minus 2. Because if it's in the denominator, you end up getting a minus when you pull it up top. So you end up getting 3 times 10 to the 1, or 30. A lot of this just comes from practice and repetition. I'm not going to do lots and lots of examples of this. One thing that is really important for you to know, though, is how to put this into your calculator. Obviously, it's much, much better if you can do it in your head. If you can do it in your calculator, well, I think it's more important if you can do it in your head, because it really shows an understanding of all the things that tie this together, the mathematics as well. But oftentimes, you will need to put things into your calculator. So let's say you have a number that you want to put into your calculator. That number could be 2 times 10 to the 3rd. Well, there's a button on your calculator that says either capital E or 2 capital E's. Not lowercase, it's got to be capital. And you can use that as a times 10 to the something. So if you do 2E3, that's the same as 2 times 10 to the 3rd. However, if you put this into your calculator in a big mathematical calculation, sometimes it doesn't work out correctly like this because people don't have parentheses in the right places and stuff like that. So generally, using your calculator, it's much better and much safer to do it like this, 2E3. It works out much, much better. So if instead of times 10 to the 3rd, let's say your number is 5.37 times 10 to the negative 3, you can just do 5.37 e negative 3. And your calculator knows how to process this. And then you can multiply it by another number, 2e7, for example. And your calculator will get this right. It knows the e means times 10 to the. Sometimes if your button has 2 e's, it might only show 1 e on the screen itself. If you got any questions, feel free to ask me or bring your calculator to me and show me, and I'll make sure you get it right. It's on different places on different calculators. Sometimes you need to hit the second function button or even the third function button. So, I think that's enough for scientific notation. Significant figures. The good news is that I don't really enforce significant figures too much, but you really should know what they mean. So significant figures is basically a way of evaluating how accurate a measurement really is. So if we have a number and we do a calculation and your answer is 5.44444444, I mean, is that really how accurate your measurement is? Because most measurements might not be this accurate. You know, let's say that you measure, I don't know, 3 jelly beans, and those jelly beans end up being 10 centimeters long. You want to find the length of each jelly bean, you can say 10 centimeters divided by 3 beans, and you end up getting 3.33333. You can use the bar sometimes. I never use the bar. But you don't know if each jelly bean is actually 3.33333 centimeters because, I mean, the jelly beans could be slightly different sizes, and your measurements, I mean, your measurement is only 10 centimeters. Like, it's not any more accurate than that. So this is where you get into significant figures. And I just want you to think carefully. You'll tend to deal more with significant figures when you take chemistry or higher level physics classes, perhaps. But the whole idea is this, is that each number has a significance. So if you have 4 digits of significance, that would be 3.33. 3 digits of significance is 3.3. 2 is 3.3. Or 1 is actually just 3 centimeters, strangely enough. So 10 divided by 3, 10 actually only has one significant figure in it. Because what happens is that zeros don't count towards significant figures. So 10 divided by 3 in this case actually is only 3. When dealing with significant figures, general rules of thumb are, I'm going to put a number, 5.0407, whatever. I don't know what the end. Zeros count if they are in the middle. Zeros do not count if they are at the end unless there's a decimal point there. So this number, 5.04070, has 1, 2, 3, 4, 5, 6. All of those numbers are significant. So this has 6 sig figs. The number 5.0407 has only 5 sig figs. If I were to write this without the decimal point, though, let's say I did 5.04070, we ignore all zeros if they are not after the decimal point. So this number actually only has 5 sig figs, which is the same number of sig figs as this number, 50407, also 5 sig figs. And once you figure out the number of significant figures in your measurement, the question is what to do with them when you're adding or multiplying. Again, I don't really tend to enforce this, but it's good for you to know. So let's say you have a number that has 3 significant figures, and you multiply that by a number with 2 significant figures. So let's say you have the number 101. Yeah, I'm just going to make this easy. Let's do this 111, and you're multiplying it by the number 22. 111 multiplied by 22. This has 3 sig figs and this has 2 sig figs. If you were to put this into your calculator or figure it out by hand, you end up getting 2, 2, 2 plus 2, 2, 2. So you get 2, 4, 4, 2. But when you're dealing with significant figures, you're actually going to only use your answer that has the same number of significant figures as the smaller of these. So if that has 3 and that has 2, your answer should only have 2 sig figs. So instead of 2442, it becomes 2400. Or 2.4 times 10 to the third. 2 sig figs. The same technique is true with dividing. So when you're dividing, you look at the minimum number of significant figures, and that's what your answer should have. The exception to this is, let's say you're dealing with whole numbers that are exactly whole, like 3 jelly beans, for example, or you're dealing with the circumference of a circle, and you say the circumference is 2 pi times the radius. Well, if 2, you look at the number 2, you think it only has 1 sig fig, and your answer should only have 1 sig fig. That's not correct. 2 is considered this kind of whole number, so you ignore the number of significant figures it has. So your answer really only has the same number of significant figures as your radius. So if your radius is 3 sig figs, your circumference should have 3 significant figures. When adding numbers together, you got to look at the decimal point. So if we add 111 plus 22, you want to really look at the number of sig figs before and after the decimal point. So 111 plus 22, they end in the same place, so 3, 3, so the answer is 133. Now let's say you added the number 111.5. Now let me change that just to make it easy. 0.337 plus 22. Your answer would be 133.337, but you can really only have an answer that goes up to this point, the decimal point. So your answer will actually still be 133. Now if that's a 1, 22.1, then your answer is 437. But now you only have one spot after the decimal, so you got to ignore the 37, and your answer is 133.4. The one main thing I ask for with significant figures is just don't give me really, really, really long numbers of significant figures, because I don't want to see that 10 divided by 3 is 33.33. I mean, you can just do 33.3. Get about the right number of significant figures. I guess when I'm talking about this as well, I would encourage you to, and I'm going to write this down also, please use decimals. Right? I don't typically want to see fractions. I don't want to see an answer that's 10/3 of a meter. Don't give me that. I much prefer to see 3.33 meters or whatever it works out to be. I like decimals. I think that's it. So thank you for this video, and this is the end.